Michael Levin is a developmental and synthetic biologist and professor at Tufts University. He has made some very important contributions towards understanding bioelectricity and the role that plays in developmental biology, in regenerative medicine, in cancer research, and he's also very interested in the foundations of cognition. He's interested in diverse embodiments of cognition, sort of the scalability of cognition, all the way from gene regulatory networks to bioelectricity to behavior and psychology and beyond. And also in synthetic, engineered cognitive systems. I'm really intrigued by the foundations of cognition, cognitive science. I think it really holds the key to understanding some very, very puzzling, deep problems. Here, we start off by getting a quick rundown of bioelectricity and the role that it plays in developmental biology. And then we go on to talk about some more foundational problems in cognition and cognitive science, including the scalability of cognition, consciousness, a bit about goal directedness, and the role that has in explaining the idea of identity. This is my conversation with Michael. Just to start off, maybe just to orient the audience, do you mind introducing how bioelectricity, bioelectrical states ended up playing a role in developmental biology to sort of change the conventional wisdom of how gene expression determines everything?
Yeah. Well, I mean, one thing to keep in mind is that I'm certainly not saying that gene expression is not important. Absolutely, it's a required component of this, and so there are kind of three streams of three main streams that are really critical to setting up any kind of patterning, which is biochemical signaling, including gene regulatory networks and transcription, and then there's biomechanical signaling, and then there's bioelectricity. So all of these three things are important, and they all sort of interplay back and forth to implement this cooperativity among cells to build the body and various parts of it. The interesting thing about bioelectricity is that, much like in the brain, it plays, I think, a rather unique role, although it's possible that someday people will find that some of the other modalities do it too. I think evolution really likes to use bioelectricity as a computational medium. So if you think about what happens in the brain, I mean, a lot of this can be actually nicely visualized by thinking about the brain and then loosening some constraints. So we think about what happens in the brain. You have an electrical network, and this electrical network allows very rapid learning, decision making, memory, preferences, goals, these kinds of cognitive things. And then the electric circuits have their say, and then this gets transduced into neurotransmitter movement, other second and messenger cascades, and eventually changes in gene expression in the brain. But these are all, sort of slower downstream steps where a lot of the initial computation is done at the electrical level, right? So the rest of the body is basically very similar, and that's not an accident. It's because I think that these bioelectrical dynamics were the evolutionary precursor of what we see in brains and neurons. So I think what evolution did was basically speed optimize these dynamics that had always been going on since the time of bacterial biofilms. So I think if you zoom in on a single cell level, what you see is electrical properties that become transduced through one of half a dozen. We know about half a dozen transduction mechanisms. They become transduced into changes of cell behavior, including transcription changes, including cell motility, cell shape, apoptosis in some cases, proliferation, all these things. So that's if you zoom in at the single cell level. If you take a step back and ask, what is the bioelectrical layer doing? Well, it seems to be doing a number of computations that have to do with making decisions at the tissue and organ level. So it decides things like, if you're a regenerating planarian, how many heads should we have? If you're a developing frog face, where do the eyes go? How many eyes? Where does the mouth go? Right? Those kind of decisions. So that's, our goal is not only to understand the molecular details of transduction at the single cell level, but to take a step back and crack the code on a tissue and organ scale, and to say, how is it that specific bioelectrical pre-patterns map onto changes of gene expression and anatomy that follow them?
Right. Was this a surprise to you? Because I mean, in a way, this has to have always been around. They're far older than human brains, but is it a surprise to you how successful the research has been, and and how far it's developed?
In the details, absolutely. So I'm always stunned when I see, new examples of bioelectric pre-patterns, when we develop new control modalities where we can make something new phenotypes, and we can make something cool happen or repair a defect. That to me is the most amazing as. So those things kind of surprise and shock me every day. On the other hand, I started down this road. Basically, my first thoughts about this kind of stuff was when I was probably 17, coming across Becker's Body Electric book and starting to think about whether these things were not just another piece of physics, but actually the information carriers that might have been what the medium by which the body processed information before brains and neurons. Like that's something that's something I've been thinking about for many years. And so from that perspective, it's kind of it didn't really fall out of the blue because I've been sort of working toward this. But I'm shocked every day when I see these things actually working. It's just, it's amazing.
Right. One of the most insightful points that I take away from your work is how bioelectrical mechanisms aren't novel to the brain.
Yeah, right. I mean, it's interesting in a couple of ways. On the one hand, certainly, uh, there's a lot of focus on, for example, if you on in neuroscience, of course, on neurons and on spiking and so on. But people who study fertilization, physiology of kidney, inner ear, of a gut, these kinds of things. I mean, those folks have been studying electrical circuits for a long time, and of course, there's a whole literature on developmental bioelectricity going back. I mean, some of the first experiments are in the early 1900s, and then there was a kind of a wave of research in the 30s and 40s, and then again in the 60s through the 80s, and a lot of it got sort of deprioritized when molecular genetics came on the scene, because doing biochemistry is easier because you can work with dead cells and tissues. You can right, grind them up and extract the DNA and protein. This stuff is hard. This bioelectricity you can only see in the living state. So so a lot of that information has been around, but you can also sort of reach a lot of this from first principles if you just ask yourself, well, where did neurons come from, right? And now we're starting to see that all the machinery, ion channels and synaptic machinery and neurotransmitters and all this, they're ancient, and they were even in the kind of in our unicellular ancestor already had a lot of this stuff, right? So you can sort of then naturally start to ask the question, okay, so and by the way, some very beautiful work in bacterial biofilms now from Godel lab. So yeah, if you just sort of ask yourself, what are the evolutionary precursors of the kinds of tricks that the brain is able to do, then it becomes kind of natural to think about it.
Right, right. I read something about how you found different types of memory in just gene regulatory networks, um, which was very surprising.
Yeah, this is a different kind of line of research for us because it's not bioelectric in any way, but the majority of our lab, in fact, the central theme of our lab is looking at cognition in unfamiliar guises. So we're interested in understanding different aspects of mind, of intelligence, of problem solving, and in all kinds of weird implementations, right? So bioelectricity is great because it really helps understand the story of how individual competent cells work together to be a higher level agent that solves different problems in morphological space, for example, instead of cellular or physiology space. But there are other architectures that do this too, and gene regulatory networks, of course, are very popular in terms of in standard developmental biology and so on. And what they illustrate now, but also we are not the first person, we are not the first to realize that gene regulatory networks can learn. So Richard Watson and a few other people have had papers on this for a long time. What they help us see is the kind of folly of making assumptions about levels of agency of something before you check it. So if you look at a gene regulatory network model, you would say, okay, look, this looks just like a piece of chemistry. I can see everything that's happening here. There's no magic. Or this thing is going to be basically at the level of a mechanical clock, right? That it's a deterministic piece of physics, and that has medical implications. It means that if I want to change how this works, I have to manipulate the hardware. I have to remove nodes, add nodes, change promoters, add new genes, and so on. I have to change the topology of the network. So but that's a really limiting assumption, because if you don't sort of assume that zero level of cognitive capacity here, but you actually say, well, let's find out, let's see what it can do. What you can then discover, and what we did, was to actually probe something like I don't know, 50 or 60 existing biological gene regulatory networks, compared with random ones that you just make up for controls. And you simply ask the question, can they learn from prior experience? And the GRN experience means a stimulation of one or more of the nodes. And so having had that experience, what do they do later? And what we found is that we can actually make a taxonomy of 6 different kinds of learning, including habituation, sensitization, and remarkably associative learning. And we found that even GRNs are capable of, if you look at them the right way, meaning if you choose the right nodes for your stimulus, your conditional stimulus, your unconditional stimulus in your response, if you look at them the right way, you discover that, yeah, they can do associative learning. It's amazing. And so that it tells you 2 things. It tells you, number one, to be really careful when making assumptions, because some things are smarter than you think they might be. And so it's an empirical question. You have to check. You can't just sort of assume or have feelings about it. That's the first thing. And the second thing is, it gives you a really interesting new way to think about how to use drugs, because this idea, right, that you find a dose and you put the patient on that dose, and then you sort of stay there and hope for the best. That's in many cases, that's not going to be the best way to control the pathway. The better way would be a timed pulse stimulation, where you're literally trying to behavior shape it's behavior shaping, it's not rewiring at that point. So that's a completely different way. And we're certainly working now on those kinds of applications.
Right. So, like thinking about the foundations of cognition, bioelectricity or gene regulatory networks are widely used because we have the understanding, the work is set out, and we have the technology and tools to intervene there. But in principle, they're not privileged levels of substrate. There's no such thing as a privileged substrate. It's just what's convenient given the reality of it. Is that sort of
Yeah,
right?
I think you're right. I think there's 2 levels of convenience here. There's what's convenient for us as scientists, in that there's an old saying, I don't know who said it, but the show me the net that you're using to fish, and I'll tell you what fish you can find, right? So they're convenient for us, meaning, yes, we found them. Who knows what else we're not finding, because it's not convenient. It's an alien form of cognition that we're just not good at noticing. It keeps us humble. It should keep us humble about that. The other thing, though, is that clearly evolution finds it very convenient. So, for example, bioelectrics is an amazingly convenient interface that cells and tissues expose to whom? To us as engineers, but also to evolution itself, to each other, to other cells, and also to parasites and conspecifics and various other things that might exploit them. But you're right in that I don't think there's anything magical about either bioelectrics or GRNs. They're just the examples we understand now, and it's entirely possible that, for example, there's a few people that have done some amazing work on networks of springs, and literally just springs. And so Christopher Buckley and Richard Watson have been studying various kinds of learning and behavior in networks made of springs. And for all we know, there are other architectures that exploit biomechanics, magnetics, optical phenomena. Who knows, right? In the wide universe, I mean, there's probably many other substrates.
Right. So there might be like principled limits as to how far we can look at the substrates, like Godelian type of limits, as we can only scale up to a certain extent just because we might have some epistemic machinery that stops us from going further.
It's entirely possible. I mean, it's the problem of giving an IQ test to somebody who's smarter than you, right? It may be really hard, right? It might be really hard for us to recognize new kinds of intelligence. It's related to the problem of hierarchical nested intelligence, which I'm also really interested in. You know, individual cells work together to form larger agents that solve larger problems. They form tissues and organs, and individuals form collectives and ant colonies and things like that. One might ask, as an individual, can you tell if you are part of a larger system like that? And if you can, what might the goals of that system be? Now, I think you're right in that there are probably serious Gödel type limits as far as really being if you're really just a piece of the machine to really understand what the collective is doing, we probably cannot understand that. But you might be able to gather evidence that something like that is going on, right? If your action space is being distorted, you might be able to gain evidence that it's not being randomly distorted. So I like to think about this as a imagine for the moment that you're a neuron in a neural network that's being trained, right? And so if you could, and I know I'm mixing metaphors here, but if you were smart enough to ask the question, you might ask yourself, do I live in a cold mechanical universe that doesn't care what happens to me? Or do I live in some sort of mindful, bigger picture universe where there's a bigger picture and a grand design of some sort, right? So humans argue about this all the time. Some people say, no, we're sort of cogs in a mechanical machine, and other people say, no, life teaches me lessons, and I feel like there's a greater pattern, right? So if you think about that from the perspective of a neuron, if that neuron were to conclude that the universe that it lives in is a sort of a zero agency sort of cold environment, it would be factually wrong. Because in fact, right, because as the network is being trained for certain things, so you could imagine, certainly it can't have a good understanding of what the goal is, but it might, as these waves of back propagation and sort of external tuning of the wash over it, it might realize that, certain things get rewarded and punished in this world. And maybe there is, right? Maybe there is some kind of a purpose to what's going on that is different from just randomness. So I don't know, again, I think it's a good, there are certain, I'm sure there are Gödel limits, but we might be able to get at least probabilistic evidence that something is happening to us.
Right, right. No, that makes sense. Okay, so just for the audience, do you mind introducing this notion of a multi-scale competency hierarchy architecture and what role that plays in getting to the foundations of cognition?
Yeah. The multi-scale competency architecture is basically this notion that in biology, and there's no reason why we can't it's not uniquely biological. I mean, today it is, but in the future, there's no reason why we can't, as engineers, all can't use this. Is this idea that we are not only nested kind of hierarchical beings in a structural sense. So we all know, there are chemical networks that make up cells, that make up tissues and organs and so on. So there's this hierarchy, but it's not just a structural scale hierarchy. It's a hierarchy in which every layer and component of that hierarchy is itself a goal-directed agent, meaning that it has some competency. It may be very profound, maybe very, very, very subtle competency to solve problems in some specific space. So there are cells that solve problems in metabolic and physiological spaces, and then there are tissues and organs that solve problems in anatomical morphospaces, and then they give rise to a human, for example, that or any other motile animal that might solve problems in three-dimensional space. And maybe later you learn to operate in linguistic space, and who knows what else there is. So this has many profound implications. I mean, one implication is that well, oftentimes people will make this distinction. They will say, well, there are collective intelligences, right? So ant colonies and termites and bird flocks and so on. And then there are real intelligences like me. And so then maybe I consider a termite mound a real, a collective intelligence, and maybe I don't, but you have to make the case that this is like a real entity aside. Well, the thing is, there are no all intelligences are collective intelligences because all intelligences are made of parts. There is no such thing as this like immutable diamond of intelligence that is like a single indivisible thing. It's impossible. So we are all, you and I are bags of cells, basically, right? We are all made of these competent little pieces of components that are neurons and other things. And the big puzzle here is to understand how the competencies of the individual parts give rise to a whole that to the next level up that has goals and competencies in a completely different space. And right, and okay, so that's one kind of implication to really understand that there are no non-collective intelligences. We are all made of parts. The second implication is for engineering. You can ask this question. I sometimes give a talk called "Why don't robots get cancer?" So you can start thinking about this idea that right now, the way we build most of our technology, you hope, let's say some sort of autonomous robotics, you hope that there's some intelligence at the higher level, but the parts are completely passive. The parts are not doing anything, right? For by and large. I mean, of course, there's now efforts in smart materials and things like that. So the good news is that you never face the problem of robot cancer, meaning that the parts are never going to go off and do something different because they have their own agenda and the coordination is broken down. So that's good. And so that makes them more predictable and maybe a little more boring. The bad news is that, and we can talk about this. Some of the most amazing properties of living things come from the fact that all of these levels are cooperating and competing against each other. So the fact that there are multiple levels that solve independent problems is hugely important. And so that leads me to the third implication, which is for evolution. Now, I'll just give you a very simple example. We've shown that if you have a tadpole and you put an eye on its tail instead of in its head, those animals can still see. The eye can connect to the spinal cord. The brain can recognize information coming from its tail somehow, and those animals can still see. Similarly, if you make a tadpole where the craniofacial organs are scrambled and the mouth is sort of off to the side, during the steps towards metamorphosis, all of this stuff will sort of rearrange, and you'll get a pretty normal face out of it. Those now, what are those? Those are competencies of the individual organs. It means that if you induce an eye on the tail or a mouth off to the wrong place, they have the competency to still get their job done. The cells will do what they need to do to get as close to normal as possible. This has massive implications for evolution, because if you didn't have this, if you had an organism that was basically Lego, right, where every piece just goes exactly wherever the genome to put it, that's where it goes. Okay, and I'm not sure there are any organisms like this. Maybe C. elegans, maybe, I'm not sure. But if you had organisms like this, then anytime you had a mutation, let's say that you had a mutation, and like all mutations, it does multiple things. Let's say that it moves the mouth off to the side, but also does something useful somewhere else. Well, evolution would never get to see the useful part because that animal would starve and the fitness is zero. And as you would expect, most mutations would be negative. They would be deleterious. And so the search space, right, that evolution would have to search would be really rugged, because you would have to wait until you found a different mutation that did the good thing but not move them out. That might be very hard. It might be impossible. Okay. However, in contrast, imagine that you had an animal which is much more realistic, where the parts had some competencies, and so now this mutation shifts the mouth or the eye, and it also does something else. Well, now those parts will get back to where they need to go. They will be functional. So now evolution gets to explore the other consequences of that mutation. So by having the parts be competent, it greatly smooths and alters the landscape of that evolution has to search, because now all those potentially negative mutations are neutral, because the competencies of the parts can sort of make up for a lot of that. So that has a couple of interesting implications. The obvious one that's obvious and one that's really not obvious. The obvious one is that it makes things much more evolvable. And so it means that you're now searching, instead of searching a really difficult space of micro positioning of all this stuff, you're searching some kind of a reward space where it's really behavior shaping, right? Your material is not passive; it's an agential material. Your cells already have capabilities and preferences and the signal processing and so on. So what you're searching is the signals that will get them to do specific things. The not obvious thing is that by having competent parts, you are hiding a lot of information about the genome from selection. Because if selection gets hold of a pretty good individual, you can't tell whether that's a good individual because the genome was amazing, or because the genome is actually not very good, but all the parts sort of made up for it, right? So maybe the genome had all kinds of problems with where the eye is supposed to go in the mouth, but by the time selection acts, everything's where it needs to be. That sets up a positive feedback loop that becomes an intelligence ratchet, because the more competency you have, the less evolution is able to select for better genomes. And the only work that can happen at that point is to select for more competency, because you can't select for better hardware because you don't see the hardware. You don't see the genetics that specify the hardware. But what you might be able to do in evolution is to improve the competency. And so therefore, there's this kind of runaway effect where I think that's and if you want to talk more about this, I have an example with planaria that I can illustrate this. But the idea is that it just sort of selects for this incredible competency of morphogenesis that is able to make up for all kinds of perturbations and so on for this reason.
Is that sort of a signifier of intelligence that you're using? The ability to uh, solve whatever goal is at relevant at that level, despite all sorts of changes, all sorts of challenges?
I, Yeah, I mean, so of course there are many definitions of intelligence, and I'm not saying mine is the only one. There are many good ones, but the one that I like that's appropriate for our work is one that William James pulled out, and his idea was basically the ability to reach the same goal by diverse means. So that's very interesting. But it's a very interesting definition because it's agnostic about all the right stuff. It doesn't mention what you have to be made of. It doesn't mention that you have to have a brain. It doesn't mention how you got here. So whether you were evolved or designed or some combination of both, it doesn't say anything about any of that. What it does is it focuses on a very kind of cybernetic notion, which is that you have the ability to achieve some sort of preferential state, whether you start in different other configurations. And the thing that the control knob that we get to twist, well, there's three of them. The first one is how much competency do you have? So you could have very low competency. You could be a ball rolling down the hill, and about the only thing you know how to do is minimize your potential energy, and that's it, right? So, or you might be really clever and some sort of autonomous vehicle, or an animal or a human. There's all kinds of different gradations. So what competencies do you have? And then, of course, you have to specify the space in which those goals exist, right? And then you have to specify what the goals are. And all of these things are empirical. They're not, this isn't philosophy. You can't just make this up. You have to make hypotheses about this and then do the experiment and see what competencies does your system have to reach those goals in that space.
Right. So just a kind of conceptual question. Thinking about cognition, intelligence, memory, these things, how people often think of it as, I'm just taking a shot at it. I think there's a lot of diverse ways how people think of cognition, but think of cognition as sort of a container for information processing systems, and then things like intentional intelligence or memory or perception seem to be added on properties of information processing systems. Is that, do you think, conceptually helpful in how to think about cognition, or would you change anything there?
I like sort of the active inference approach, kind of like Carl Friston's sort of stuff, where it's really very much at the beginning. So it's like already very simple physical systems have some ability to minimize certain quantities and to do some amount of active inference about what happens next. And so on top of that, and so I can, I can sort of tell a story if you want. I can tell a story about how I think minimal agents arise from nothing, basically. But all of the capacities that we think about, so memory and preferences, and then metacognition that lets you change your goals and so on, and then planning, and then who knows what else, right? All of these things sort of are scaled up versions of very simple things that really minimal agents are doing. So I can tell stories about metacognition in bacteria, and I can tell stories about a sense of free will in extremely minimal kinds of systems.
Right. So where, yeah, how do you address the question of where it starts? Like, is there a bottom out somewhere where there's zero cognition? I know that question is very annoying to deal with because both answers seem unsatisfying, right? Like, it seems unsatisfying to say that, oh, there's a point where it's just physics and it stops and it becomes alive, but it's also kind of ridiculous to go the other way, where you say everything is alive in some sense. So yeah, how do you deal with that?
A couple things. I'm not going to say anything about what's alive because I actually don't know of a good definition for that, and I spend no time thinking about the definition of life. Other people do, so it's a fine question, but I don't deal with that. I deal with cognition, which the question of how that overlaps with a set of things that are alive, I have no idea. So, but let's talk about cognition. Does it go all the way down? So I'm not sure. I'm not sure yet. However, I lean strongly towards the answer that in this universe there is no zero, that it does not go to zero. The reason is twofold. Number one, Uh, imagine if I said to you, let's come up with the most minimal versions of what cognition would have to be. Like what's the most minimal capacity or criteria that which you would have to have. So if I think about what the most minimal capacity is, I would say it has to have two things for to be on the cognitive spectrum. It has to have two things. One is it has to be able to take actions that are not fully determined by local circumstances. That means that, right, if you're a billiard ball, the only action you're ever going to take is if you're giving a push, if you're given a push by something else. That's why you're acting, right? There's nothing that happened 3 days ago that matters. There's nothing that happened, that's going to happen in the future that matters. It's nothing that happens, far away that happens. It's everything's pretty local. But the ability to act with some dependency on either future states, if you're really cognitive to be able to anticipate things, or events that happened a long time ago, or events that are far away. Any ability along that axis raises the chance that you're actually cognitive. So you have to have some ability for non-local decision, non-local action. And that's the first thing. And the other thing is, I would say there has to be a reasonable story that could be told about you being a goal-directed agent. So there has to be a way to look at the system where it looks like it's pursuing some sort of goal with some level of competency, if it extremely low, but some level. So having put out those two criteria, I now you realize that elementary particles already do this. So you have quantum indeterminacy, which tells you that they have this. Now, it isn't in terms of unpredictability. So you have fundamental unpredictability. Now, it's random, which is not what we want for advanced cognition. You don't want to be a random agent. That doesn't really help. But the fact that it is not fully locked down by local conditions gives you that nano, sort of minimal level of free action, right? That you could ask for. I don't know what else minimal freedom would look like if not that. And the ability to pursue goals again with least action principles. You already see that there is this like extremely low level, but not zero ability to pursue goal states. You see it in photon paths, you see it in rocks, whatever. So, of course, what biology does that's really amazing is scale those up in a way that just being a pile of rocks does not. Uh, so that's my one reason for thinking that there's no zero, because as I think to the most minimal things in the world that we know of, they seem to already have it. That's the first thing. The second thing is, as you pointed out, that it's kind of unsatisfactory in both ways. Uh, I think the right way to think about this is to go backwards. If you start with it, so a lot of people start forward, meaning that they'll say, I just can't imagine that paramecia have hopes and dreams like us. Well, you have to do two things. First of all, of course, you scale down your expectations. No one is saying that paramecia have hopes and dreams like us, but most capacities have come from simpler versions of those capacities. And the way to think about this is not to start with paramecia and go up, is to start with you and go backwards. So assuming that you and I believe that whatever cognition is, we have it, we have something, otherwise the word means nothing. So we have something. So now let's just start walking backwards. So you walk backwards to when you were born, and you walk backwards day by day, minute by minute, and eventually you get to a spot where you are an unfertilized oocyte. And if having gotten to the position of an unfertilized oocyte, you say that, okay, all I see is physics and chemistry. I see zero cognition here. Then you have to tell me, well, at what stage? Remember, we started at some reasonable level of human cognition. When did it wink out? If we get to zero, you have to tell me when it disappeared. And I mean, people, people will pick lines that are convenient for running a society. So they will say, you have agency when you can sign a contract, or when you can rent a car, which is, by the way, older than when you can vote. It's interesting, right? And going backwards. But all of this, but we know all of this is baloney, in the same way that reaching maturity on your 18th birthday is baloney. Does anything happen when the clock ticks over to 18? No, of course not. We know that. It's just convenience. So I have never heard, despite people talk about phase transitions and this and that, I think if we take development seriously, developmental biology, and we see how slow and continuous that process is. There's literally nothing that is sharp that sort of ticks over. You say, oh, well, look, on day 17 of development, this particular thing just boom happened. I mean, that just doesn't happen. So I've never heard of a convincing place to put any phase transition like that, anything that's sharp like that. So that leads me, I don't know of any way out of this. I think there's got to be cognition I think it has to be a continuum, and I think it has to go all the way down. Can I prove that there's no phase transition that happens when the 10,000th neuron sort of gets born? No, I can't prove that, but it's completely implausible to me. And I've seen no story like that makes any sense.
Yeah, I mean, I think the approach of going backwards has to be more helpful because it's empirically falsifiable. You can
That's
deal
right.
with it empirically versus uh, I feel like whenever people sit down and make definitions for what this is what life should be, this is what cognition should be, and then let's go progressively find examples of it. It never tends to work out. You can always find counterintuitive examples that throw the whole paradigm out.
Exactly, exactly. And I think that developmental biology and evolution too, uh, because you can go backwards that way as well until you get to whatever was here before archaea. Um, if you take it seriously, it's sort of the ultimate. It's to me, it's the most magical of all the sciences because you get to see in front of your eyes, you get to see the journey that we all take from physics to mind. Like that's it. You just see it right there. You start with a pile with a pile of chemicals, and you end up with something that's going to make grand philosophical claims about being or not being an agent and so on. And so that is a slow process. You can watch it happen. It's amazing. That is where all the insights should come from.
As we begin to think more about nested hierarchies and synthetically engineered cognitive forms, I think those distinctions are going to get even more loose and confusing. You won't be able to have that simple test of this thing is alive or sentient or cognitive, and we should treat it ethically, and then this thing isn't, and we shouldn't.
I completely agree. What all of what I mean, science fiction, our authors have been talking about this for the longest time. But right now, both developmental biology and synthetic bioengineering are highlighting the fact that the categories that we used to use, so these binary categories, they were never any good, but they're definitely not good now. They used to be sort of okay heuristics because back in the olden days, you could walk up to something and you could sort of knock on it, right? And if you heard a metallic clangy sound, you could conclude that okay, this thing came from a factory and it's got it's got basically zero or near zero agency, and I'm ethically it's permissible for me to do whatever I want and take this thing apart. If you sort of knock on it and it's kind of furry and soft and wet, you would conclude that this is the product of biological evolution and I'm supposed to be nice to it and so on. Now, yeah, of course, the science fiction authors have pointed out for many decades that yeah, that only works with an n of one example here on Earth. If something lands on your front lawn and this thing sort of trundles out and it's kind of like metallic looking, but it hands you this poem that it wrote and about how happy it is to meet you. Like, what are you going to use to decide what your responsibilities here are? I mean, we're completely at sea here because our categories were terrible because really our binary definitions of robot, of organism, of being, this idea that our ethical norms are somehow tied to a one particular path that phylogeny took here on Earth, and that we're gonna look at how much your brain looks like the human brain, and then we'll decide. I mean, this was never good, but it was good enough for a while to sort of keep things rolling, but all of that, none of that stuff is going to survive the coming decades. We're going to need, for sure, we're going to be surrounded by uh creatures that defy description using old categories, and the ethics is going to have to keep up with that.
Yeah. Just a silly aside. Have you seen any fiction or just popular media where you like it, like where you think that it does justice or asks interesting questions?
Yeah, I should clarify, I wasn't down on sci-fi at all. I think sci-fi has done the right thing in bringing up all these crazy corner cases, and it's the ignoring of all that by scientists That's really the problem. I mean, I really like, I mean, one of my favorite authors is Stanislav Lem. And in his, I think that's good. And also, just kind of out of the popular, more popular repertoire, the cantina scene in the original Star Wars, right? This like just incredible mix of crazy biologicals, different different robots running around, the things that look like a footstool on wheels, and then there's C-3PO with existential concerns about life and whatnot. Like that there. What you don't have, which I think they handled it way better than, for example, in Star Trek, right? If you watch the new, well, it's not new anymore, but the next generation Star Trek, right? They had no end of debates about, oh my God, what is Data? Is he this? Is he that? Star Wars didn't have any of that. Everybody knew that, right? It was all, you have this giant spectrum. There were every crazy creature under the sun was there. You had your androids that you had relationships with, and of various kinds, and there were nobody, right? So they spent zero time figuring out whether C-3PO had a, was this or that, that's what I think the future is going to look like. I think we are going to transition the young people. I think the young people today have very different attitudes than a lot of the older folks about this stuff. They're gonna have no problem recognizing that some of these things. Look, I don't know why. Fundamentally, I hear all the time that this is a living organism. The majesty of it. We can't possibly. What is it? Why does the process of evolution, which is basically this like a meandering hill climbing search over phenotype space, why do we think that process has a unique monopoly on creating rational agents? Why, right? To me, if somebody said, well, here's the process of evolution, which just sort of blindly pokes around, and sometimes good things happen, and then here is a set of engineers, which, by the way, can also use evolutionary search if they want to, but also they have the possibility of rational design. Which of these two things is going to come up with better cognitive agents? I'll pick the engineers every time, because right, because why would it have to only be natural evolution that can give rise to this? That makes no sense to me at all. And I think as we get better and better at capturing what it is that we mean by true agency, which arises spontaneously in this process of autopoiesis, where it's not a robot where everything was nailed down. Your structure, your structure, your problem space, your capabilities, like everything is nailed down by somebody else. That doesn't do the trick. But once we, as engineers, once we really get onto some of the things that are important about agency, we're going to be creating this stuff, these beings left and right, all over the place, and we need to get over the fact that we're going to be able to draw some kind of binary line. But it's very problematic. Look at what happened to Darwin, right? Darwin basically said, well, we used to think there are two categories, right? So kind of dumb matter, and then humans and angels and whatever. That's what we used to think. And so Darwin gave us one axis of a continuum, and everybody freaked out. And they're still freaking out about this, right? There's people still very upset about this, the idea that there's a continuum, and then you have to worry about, if we had some kind of early hominid, what would your responsibility to it be, right? Like, who knows? So that's already a problem. Forget that one axis. We're going to have an option space, a hugely dimensional option space of every possibility of biological, of synthetic material, of software is going to be some kind of agent, and we're going to have to, yeah. So to me, I don't know. To me, the and there's another piece. So I guess the cantina scene is the one that I always think of. The other thing that was kind of cool, and I didn't watch the whole show, so I have no idea what else happened, but I just remember one scene out of Westworld. There's a show Westworld on HBO, right? And there's this one scene that I thought was pretty good, where one of the androids is malfunctioning. So they say, we're going to take you in for repairs. And when they take it in for repairs, what does that look like? Well, it's a room, there's a couch, and there's a guy with a clipboard, and he says, okay, lie down on the couch, tell me what's bothering you. That's how you go for repairs. And that makes perfect sense, because when you get to the point of complexity that you are able to carry on a sophisticated interaction with human clients or whatever it was, by that point nobody's fixing you the way that they would fix a vacuum cleaner with screwdrivers. At that point, you may have existential angst and phobias and who knows what the heck else, that probably where the repair process probably looks like more like psychotherapy than it does like anything else. So I thought that was a pretty good yeah, that was a pretty good take on it.
Yeah, 100%. I mean, it's just unimaginable. Like the possibility space of things that come, it's just unimaginable. Like one thing that threw me in preparing for this was, I know you don't like to talk about consciousness because of all the confusion, but talking about what the conscious experience of development would be like, not just what the conscious experience of this complete organism is, but what does it feel like to be a fetus and a developed child? I mean, even that's unimaginable, let alone the possibility space of possible cognitive agents.
Yeah. Yeah, I mean, we have some examples right here on Earth that have to do with so for example the caterpillar butterfly transition, right? So never mind what is it like to be a butterfly? What's it like to be a caterpillar becoming a butterfly when your brain is literally dissolved into most of the cells die, all the connections are broken up, a completely new brain is built, which by the way contains at least some of the original memories. So that's the thing. You can train caterpillars, and the moth or butterfly will show the information, show evidence of retention. So there's some fascinating questions of personal identity. I mean, if the memories carry over, then there's some identity, some cognitive identity there. What does that feel like? And so the thing with what this whole issue of what's it like is really important because it shows us the problem with consciousness. The problem with consciousness, the hard problem is that for every other type of question that we may have a theory, and those theory and what we know, we may not know if it's right or wrong, but what we know for sure is the format in which those theories give answers. So for example, if you're going to have a theory of gravity or a theory of whatever, you know what it outputs. It outputs numbers that you or something like it that you can then compare with observations. That's what it outputs. So now let's ask ourselves, okay, imagine that we had a correct theory of consciousness, whatever it is. It doesn't matter what it is, but let's say, what does it output? What are the right? What format are its predictions in? Because anything that is predictions that you can compare to physical outcomes, that's a theory of behavior. That's not a theory of consciousness. That's a theory of behavior. So that's fine. What would a good theory of consciousness even output? So if I want to know what is it like to be a caterpillar or a xenobot or whatever, what is the answer going to be like? I mean, the only thing I can think of is that it's art. That it's basically the idea is that what it outputs is some sort of stimulus that attempts to put you in a similar state. So and there was a really I'm blanking on that. There was a great quote about this from somebody that to the effect that if you want somebody to what was it? If you want somebody to be scared or something, don't tell them how scared you are. Tell them something that makes them scared, right? And that basic. So the output of these things is not anything like a theory that we recognize. It's a protocol almost, right? It's here. Well, if you want to know how I feel, here do X, Y, Z, and then you will feel like I feel as much as as much as possible, right? So it's a completely different way of thinking about theories and predictions, and yeah, trying to understand what these other creatures, what it's like to be them is maybe a hopeless endeavor.
Yeah, I mean, the methods are so different, like you said. Like, I often think about like contemplative practices and meditation and the philosophy that's attached with them. It's very interesting, very fruitful. But I often think like, is it even possible to analytically understand that philosophy the way that we interact with Western philosophy, or there just the way that we go about it is totally different. Like, I don't think reading it without the practice involved really will help me understand consciousness.
Yeah, I think you're right. The other thing that makes consciousness unique is that it's one of those areas where you really can't you can't do experiments and make progress and remain the same. So in every other kind of thing, you can do physics experiments and you can do biology and behavioral experiments, and you can still be you because it's a third party kind of it's a third person kind of thing, right? I mean, you're changed a little bit by virtue of the fact that you've now gained new knowledge, you have memories, so you're changed a little bit, but it's not much. If the only way to study consciousness is to do experiments where you yourself are going to change, your consciousness is going to change, your propensity to have different kinds of thoughts in the future are going to change if you're involved in some sort of contemplative practice that where the goal is over some really long period of time, consistent effort will get me to have certain kinds of thoughts more or less frequently or whatever you're trying to achieve. Yeah, it changes the subject of the experiment. So, and I think people who are into that stuff recognized that a long time ago and pointed out that this is very different. It's a very different way of doing experiments.
Okay, shifting gears a bit. So personal identity. How is the idea of goal-directedness relevant to understanding identity?
I try to a few years ago now, I tried to come up with a framework where we could try to understand what a self is. Another way to say that is an agent of some sort. And what I wanted was a definition and a framework where you could compare in the same space selves of radically different construction and provenance. So they might, you could compare aliens and swarms and sort of conventional animals and plants and robots and you should be able to compare them all on in the same rubric. So what I came up with, my proposal was, and I'm certainly not the first person to emphasize gold, teleology of some sort as a central binding feature of a self. This idea that you are a self to the extent that you can pursue goals that are not the goals of your individual parts, and with some competency, low or high or in the middle. And one thing that defines your degree of selfhood is the scale of your goals, literally the spatiotemporal scale of your goals. And so this is I call this a cognitive light cone. This idea that now it's not how far out can I sense or how far can I act. It's how big are the goal states that I can strive towards in space and time. So you can imagine, right? If you're some sort of a bacterium, then your goal is to increase the local sugar concentration right now. And maybe you've got a tiny bit of predictive, capacity going forward in the gradient, but that's about it. If you're a dog, you have a lot more, but you are never going to care about you're never going to have a goal about anything that's 3 towns over and 2 weeks later. Like that's just not going to happen, right? You have some spatial and temporal cognitive cone within which all your goals fit. If you're a human, uniquely, you might have goals that are longer than your own lifespan, which meaning that they're fundamentally provably unattainable. So you might have goals that are enormous. They might be planetary scale goals. You might have world peace, or you want to go to Mars, or you're upset that the universe is going to experience heat death, right? So you might have these enormous goals that are your light cone might be gigantic, or maybe not. And the point is that could also possibly be the source of some of our psychoses, because we are maybe the first creature to be able to have goals that are guaranteed unachievable. Like that's a tough pill to swallow, actually, right? So we are the only ones, at least for now, that know that. So
Is there any sort of general way of thinking about how these levels of competency, these different nested hierarchies interact? That can we take any general lessons away from how, I don't know, how psychology needs to pay attention to lower level mechanisms, or economics needs to pay attention to some mechanism, or is it just a matter of, or is it just an empirical question always that you have to kind of go in and find what's relevant and operable?
I think it's largely empirical, but there are some principles we can sort of guess at. Like one principle that we're working with is this idea that the larger system is bending the option space of the systems underneath it. So in other words, if you as a subsystem are good at doing XYZ, then I don't need to micromanage how you're going to do that, but I do need to bend the reward space for you so that by doing what you're good at, you will accomplish something that I, as the larger system, want. Right, so that idea of the option space being distorted, and this has a lot of it's kind of obvious how it works for cells, but even at the larger scale, for example, you've got people who I don't know, if you're a smoker and you want to stop smoking, one thing that people will do is they'll take their cigarettes and their car keys and and throw them out the window at night, because they know that even though they're going to want to smoke in the middle of the night, it's too much effort and it's cold and they're not going to do it. So what you're doing is you've got this higher level that has large scale goals and says, okay, I really shouldn't be smoking, but you don't have direct control over the fact that your circuits in your body are addicted to nicotine. You don't have any direct control over that. But what you can do is change the energy barrier, and you can make it you can distort things in your environment that just makes that, just so you're not going to, when you get up at night, you're not going to do it. And so, right, so it's just this kind of a silly example, but this idea that it just that's how you distort the energy landscape for your other systems to reward and punish them and induce them to do various things. So the details of all of that are empirical questions, and they need to be kind of settled every time. But I think that idea that we are all navigating different problem spaces, and that our parts are good at certain things, and what you really want is for the actions of your parts to they make it easy for you not to have to micromanage stuff, right? That they're good at, and you have to distort their option space so that you can get your own goals met.
Right. So is that top-down causality then? Like it's not top-down causality in the sense that at the emergent level you're consciously moving something at the lower level, but you, if you can understand the goal-directed behavior of the lower level and somehow intervene to accomplish something, does that?
Yeah, I do think that top-down causation exists. I think that, well, the good news is that the kind of amazing now is that we don't have to guess or have philosophical debates about it. People like Eric Hole have actually developed a formalism where, at least for certain kind of systems, you can do the math and you can actually see which level does the most work. And so in many cases, it will be the lowest level, but in other cases, it won't be. So you could actually, it becomes kind of a calculable question for certain kinds of systems. But I mean, there's some amazing examples in biology of top-down causation. For example, there's this thing, in a newt there is these kidney tubules, these little tubes that go to the kidneys, right? If you take a cross section through them, you see that in normal kidney there's about 8 to 10 cells that communicate with each other, and they form a little circle, and that's the tube, right? What you can do is experimentally, and this was discovered back in the 40s, what you can do experimentally is make the cell size larger and larger artificially. As you make the cell size larger and larger, the kidney tubule stays the same. Now, how does that happen? Because fewer and fewer cells are now part of this thing. The amazing thing is that if you make the cells truly gigantic, then just one cell will bend around itself, leave a hole in the middle, and make the tubule. So now here's where the top-down causation comes in. The mechanism of a cell bending itself around is a completely different mechanism from cells undergoing cell-to-cell communication and tubulogenesis. So that means that in the service of this larger scale structure of making this tubule of a certain size, different molecular mechanisms get called up. So the idea that different, and we have other examples that I won't go into now, where the same thing happens transcriptionally, where specific pieces of the genome are used when they're needed, and so on. It's I think that in a lot of these cases, you lose a lot by deciding up front that you're only going to do bottom-up emergence as opposed to top-down causation. I think you lose on the predictive power in a lot of these situations.
So do you think like our future engineering technologies need to take a hint from this, that we need to develop, instead of developing sort of systems where just macro managing dumb parts, they need to develop these nested hierarchies that I mean, it doesn't have to be biological. It doesn't have to be transcriptional to anatomical to neural networks and so on. But our nested hierarchy is the way to go.
Yeah, yeah, it's essential. And actually, engineers are already pretty good at this. They've been building with thermostats and with things like that for a really long time. So engineers are okay with the machines that have purpose and teleology and so on. It's the biologists that are really upset about it. And I think so. Jamie Davies and I just wrote a review on bioengineering with agential materials. And I've been saying for years that the way we're going to get transformative regenerative medicine is not to micromanage the hardware of where every cell and where all the gene expressions are, but to figure out how to convince the collective intelligence of the cells to take a certain path in morphospace, basically change the navigation via resetting the goals. I mean, we've shown this experimentally in certain cases. You do much better by resetting the goals of an intelligent system like that than you will by micromanagement. So I think where the benefits will first show up is in regenerative medicine, and then synthetic engineering and so on.
Right. Yeah. I mean, I think computer scientists have a good knack for not getting tripped up over these questions because they don't care about a privileged substrate or a privileged hierarchy level. I mean, as long as the implementation works, it works.
Yeah. Yeah. Well, and they have a really great example. I mean, one of the best examples of this is if you look at a microprocessor taking instructions and executing them, right? You could try to be sort of a reductionist about this, and you can say there's no such thing as an algorithm. All there is electrons following Maxwell's laws of the electron motion. Have you ever met a coder that thinks that way? I mean, you would never be able to do anything if, right? It shows you the sterility of this view. If you want to achieve anything in this discipline, you have to take seriously the fact that the algorithm drives. It's an amazing thing. It's the algorithm, whatever the hell that is actually causally shifting electrons in different paths through your circuits. If you don't believe that, you will never build anything, right?
And that's what evolution exploits, right? Like it finds ways to build computer systems. It just finds ways to build logic gates, and that opens up expansively the space of things that can be done. Yeah. Okay. Sorry, I know we just passed the hour mark. Just two quick questions. So one thing, goals. I have to ask you, where do goals come from? Because I mean, in feedback loops, I can understand sort of simple feedback loops, but high coarse grained complex image of what should be built. How does that happen? That's yeah.
That's a really deep question, and I'm not going to pretend I have the answer to it, but I'll give a couple thoughts. The easiest way to sort of the cheap way to think about this is that, well, evolution. So evolution makes sure that we only see organisms with certain kinds of goals. Everything else that had other goals died out in the fight for survival. Okay, that's one way to think about it. However, it doesn't quite do the trick, and the reason is think about our xenobots. So our xenobots are these synthetic proto-organisms that are formed from frog skin cells that you basically no genetic modification. You take these skin cells off of a frog embryo, give them a chance to kind of reimagine their multicellularity. They form something completely different. They form this little thing that runs around and has all kinds of behaviors and makes copies of itself from loose cells it finds in the environment. So we don't know yet. It's very early days. We don't know what their cognitive capacities are. We don't know what their behavioral goals are. We have no idea. But they have capacities like, for example, kinematic replication, meaning that if you sprinkle a bunch of cells in the environment, they will run around, compact those cells into little snowballs. Those become more xenobots, and those will go and do the same thing and several generations forward. So now you might ask yourself, well, where did that come from? Where it did not come from was years of selection to be a good xenobot, because there's never been any xenobots. There's never been selection to be a good xenobot. So where does it come from? I don't know, but I think the closest, and Andreas Wagner, he has some really good books like Arrival of the Fittest and some other stuff. So I think his thoughts is the closest to mine on this, which is that I really think we're talking about here the same question that people talk about when they ask where the truths of mathematics come from. So for example, right, if you, let's say you're trying to evolve a triangle, and so you evolve the first angle and then you evolve the second angle. Well, you don't need to evolve the third angle. You already know what it is. Now, that's kind of amazing. That's a free gift. That saved evolution a ton of time. Where did that come from? So that leads the simple question, well, where do these truths live of geometry, of number theory? The fact that if you have 10 apples and 3 kids, you just simply cannot divide it evenly, right? Where does that fact live? Because it isn't the same as a lot of the other kinds of explanations we have. The fact that you couldn't do it, the fact that there's no mechanism that does it, the explanation lives somewhere in Platonic mathematical land, right? So it's a very unconvincing, unsatisfying kind of answer. But I think it's the same sort of question. I think there are what Stuart Newman would call inherent laws, which are free gifts, free lunches from physics, from laws of computation, from geometry. The fact that if as you were saying earlier, if you discover an ion channel, voltage gated ion channels are basically voltage gated current conductances, right? They're basically transistors. So as soon as you discover that, well, now you've got logic gates that you can build. Did you have to evolve a truth table for the logic gate? No. By virtue of evolving the transistor that you could make a logic gate with, you get the truth table for free. So all of that kind of stuff, who knows what else is hanging out there in this? Like, I visualize this sort of invisible, world of Platonic forms that are not passive. They are goals and capabilities that you sort of connect with by building the right physical machine that can take advantage of that. Archimedean machines, all these kinds of things that hang out there that you can take advantage of if you have the right hardware.
Oh man, that's so unbelievably hard to get to. Mathematical Platonism. It's just can't imagine a world where it's not true. Can't imagine a world where it is. It's so confusing.
Yeah, I agree.
Yeah. Okay. Final question. So you and your lab, I think, are exceptionally good at managing theoretical, conceptual work and empirical work in the space. Do you sort of have any general principles or lessons?
Wow. Yeah. I mean, it's incredibly hard to the point where I feel lucky whenever we manage to do something like that. And so I would be lying if I said I had a general kind of turn the crank algorithm by which this was. I mean, I can't even necessarily reproduce it on demand, never mind telling anybody else how to do it. Um, I do. I mean, here are my principles, and we squeeze out of them what we can. One thing that I think that I try very hard is to try to make sure that my philosophy has practical implications. So, right. So this is, for example, my approach to agency. I think that agency claims are engineering claims. I think they are claims about how to relate to systems, how to control them, predict them, communicate with them, and so on. In the sense that I don't think you should be able to have armchair pre commitments to things like, well, thermostats don't have goals. That's that's a hill I'll die on. To me, that's an empirical question, right? All of these things that you have to do experiments. So one thing I try to do is to have views that have practical implications. Not everything is testable right now, right? Of course, but everything should make some kind of contact with reality where I like theories that to me a good theory is one that opens suggests new experiments, so new capabilities, new experiments, things that people sometimes say to me. I'll give a talk and people say, I love the experiments in the data, but I wish you'd stop talking about all this crazy agency stuff. It's just, it's uncomfortable. It's probably, useless. Just do the experiments. I said, you don't understand. We wouldn't have done any of these experiments if we didn't have that way of thinking about it, right? So, to me, the ideal thing is to have a kind of a generative sort of approach to things that constantly suggests new research programs, new capabilities. So that's so we do the best we can there. But you know, the devil is always in the details. Some of this stuff is testable, some is not. And for much of it, we're not, you know, for much of it, I'm not smart enough to really know what the ideal right way to crack it right now is. Hopefully, as we you know, as we do more work, it becomes, but I am rather pleased that the way that so far we've been able to tie in some novel experimental results to these kind of theories that have given rise to them. And that makes me think, you know, that makes me think we're at least a little bit on the right track, basically.